Welcome to the channel NextGen Tech Prep. In today's video, we are diving deep into essential questions and comprehensive answers for the Google Professional Data Engineer certification. Whether you're preparing for an exam or just looking to sharpen your knowledge, you're in the right place. If you find this content valuable, please hit that subscribe button and ring the notification bell so you never miss an update. Now, let's get started.
You are testing a Dataflow pipeline to ingest and transform text files. The files are compressed gzip, errors are written to a dead letter queue, and you are using side inputs to join data. You noticed that the pipeline is taking longer to complete than expected. What should you do to expedite the Dataflow job? The options are: Option A, switch to compressed Avro files. Option B, reduce the batch size. Option C, retry records that throw an error. Option D, use cogroup by key instead of the side input.
To arrive at the correct answer, we focus on the keywords, using side inputs to join data, taking longer to complete than expected.
The correct answer is option D, use cogroup by key instead of the side input.
Why is this correct? D. Cogroup by key is more efficient for joining large P collections. Side inputs broadcast the entire dataset to all workers, which consumes significant memory and degrades performance, causing the job to take longer. Why are the others incorrect? A. Although Avro files support better parallel splitting than gzip, changing the file format does not resolve the primary architectural bottleneck caused by using side inputs. B. Reducing the batch size does not address the root cause of the performance degradation introduced by the inefficient side inputs join strategy. C. Retrying records only relates to error handling within the dead letter queue and does not expedite the processing time or improve pipeline efficiency.
You are building a real-time prediction engine that streams files, which may contain PII, personal identifiable information, data, into cloud storage and eventually into BigQuery. You want to ensure that the sensitive data is masked but still maintains referential integrity. Because names and emails are often used as join keys, how should you use the Cloud Data Loss Prevention API, DLP API, to ensure that the PII data is not accessible by unauthorized individuals? The options are: Option A, create a pseudonym by replacing the PII data with cryptogenic tokens, and store the non-tokenized data in a lockdown button. Option B, redact all PII data, and store a version of the unredacted data in a lockdown bucket. Option C, scan every table in BigQuery, and mask the data it finds that has PII. Option D, create a pseudonym by replacing PII data with a cryptographic format-preserving token.
To arrive at the correct answer, we focus on the keywords: PI, personal identifiable information, data, masked, maintains referential integrity, join keys, Cloud Data Loss Prevention API, DLP API.
The correct answer is option D, create a pseudonym by replacing PII data with a cryptographic format-preserving token.
Why is this correct? D. Cryptographic format-preserving tokens create pseudonyms that mask PII while maintaining referential integrity, allowing the tokenized data to be used securely as join keys. Why are the others incorrect? A. Storing the raw non-tokenized data introduces unnecessary security risks and storage overhead. Also, storing data in a lockdown button is nonsensical. B. Redacting data entirely destroys its original format and referential integrity, making it impossible to use the fields as join keys. C. Masking data only after it reaches BigQuery means PII is temporarily stored in the clear during transit and early storage, exposing it to unauthorized access.
You are migrating an application that tracks library books and information about each book, such as author or year published, from an on-premises data warehouse to BigQuery. In your current relational database, the author information is kept in a separate table and joined to the book information on a common key. Based on Google's recommended practice for schema design, how would you structure the data to ensure optimal speed of queries about the author of each book that has been borrowed? The options are: Option A, keep the schema the same, maintain the different tables for the book and each of the attributes, and query as you are doing today. Option B, create a table that is wide and includes a column for each attribute, including the author's first name, last name, date of birth, etc. Option C, create a table that includes information about the books and authors, but nest the author fields inside the author column. Option D, keep the schema the same, create a view that joins all of the tables, and always query the view.
To arrive at the correct answer, we focus on the keywords: migrating an application, on-premises data warehouse to BigQuery, author information is kept in a separate table and joined, Google's recommended practice for schema design, optimal speed of queries.
The correct answer is option C, create a table that includes information about the books and authors, but nest the author fields inside the author column.
Why is this correct? C. BigQuery performs best with denormalized data. Nesting related attributes, like author details, using array or struct data types avoids expensive join operations, improving query speed and efficiency as recommended by Google. Why are the others incorrect? A. Maintaining a normalized schema and using joins in BigQuery degrades query performance. BigQuery is optimized for analytical workloads, where denormalization is preferred over traditional relational schema design. B. A completely flat, wide table can lead to massive data duplication, wasting storage and processing resources compared to using nested fields, which provide a balance of denormalization without excessive redundancy. D. Creating a view still executes the underlying join operations on the normalized tables at query time, meaning performance will still suffer compared to physically denormalizing and nesting the data.
You need to give new website users a globally unique identifier, GUID, using a service that takes in data points and returns a GUID. This data is sourced from both internal and external systems via HTTP calls that you will make via microservices within your pipeline. There will be tens of thousands of messages per second, and that can be multi-threaded. And you worry about the back pressure on the system. How should you design your pipeline to minimize that back pressure? The options are: Option A, call out to the service via HTTP. Option B, create the pipeline statically in the class definition. Option C, create a new object in the start bundle method of doFn. Option D, batch the job into 10-second increments.
To arrive at the correct answer, we focus on the keywords: tens of thousands of messages per second, back pressure on the system, minimize that back pressure.
The correct answer is option D, batch the job into 10-second increments.
Why is this correct? D. Batching requests into windows, like 10-second increments, significantly reduces the number of HTTP calls. This consolidates tens of thousands of messages into fewer, larger requests, effectively minimizing back pressure on the system and preventing external service overload. Why are the others incorrect? A. Making individual HTTP calls for tens of thousands of messages per second exacerbates back pressure by creating an overwhelming number of concurrent connections and requests to the external service. B. Creating the pipeline statically in the class definition relates to pipeline construction and initialization, not runtime optimization or mitigating high-throughput HTTP call back pressure. Why are the others incorrect? C. Creating a new object in the start bundle method optimizes Dataflow by reducing initialization overhead per bundle, but it does not reduce the actual number of HTTP requests needed, failing to solve the back pressure issue.
You are migrating your data warehouse to Google Cloud and decommissioning your on-premises data center. Because this is a priority for your company, you know that bandwidth will be made available for the initial data load to the cloud. The files being transferred are not large in number, but each file is 90 GB. Additionally, you want your transactional systems to continually update the warehouse on Google Cloud in real time. What tools should you use to migrate the data and ensure that it continues to write to your warehouse? The options are: Option A, Storage Transfer Service for the migration, pub/sub and Cloud Data Fusion for the real-time updates. Option B, BigQuery data transfer service for the migration, pub/sub and Dataproc for the real-time updates. Option C, SUDL for the migration, pub/sub and Dataflow for the real-time updates. Option D, SUDL for both the migration and the real-time updates.
To arrive at the correct answer, we focus on the keywords. On-premises data center, bandwidth will be made available, not large in number, each file is 90 gigabytes, continually update, in real time.
The correct answer is option C, SUDL for the migration, pub/sub and Dataflow for the real-time updates.
Why is this correct? C. SUDL is ideal for migrating a small number of very large, 90 gigabytes, on-premises files. Pub/sub provides scalable message ingestion, and Dataflow is the standard, fully managed tool for processing real-time streaming data into Google Cloud. Why are the others incorrect? A. Storage transfer service is optimized for large-scale migrations, millions of files, not a small number of large files. Cloud Data Fusion is less suited for continuous real-time streaming than Dataflow. B. BigQuery data transfer service is designed for scheduled transfers from SaaS applications, not on-premises files. Dataproc is not as optimal as Dataflow for fully managed, real-time streaming updates. D. While SUDL handles the initial file migration well, it is a batch command line tool and is completely incapable of handling continuous, real-time streaming updates from transactional systems.
You are using Bigtable to persist and serve stock market data for each of the major indices. To serve the trading application, you need to access only the most recent stock prices that are streaming in. How should you design your row key and tables to ensure that you can access the data with the simplest query? The options are: Option A, create one unique table for all of the indices, and then use the index and timestamp as the row key design. Option B, create one unique table for all of the indices, and then use a reverse timestamp as the row key design. Option C, for each index, have a separate table and use a timestamp as the row key design. Option D, for each index, have a separate table and use a reverse timestamp as the row key design.
To arrive at the correct answer, we focus on the keywords: Bigtable, most recent stock prices, design your row key and tables, simplest query.
The correct answer is option A, create one unique table for all of the indices, and then use the index and timestamp as the row key design.
Why is this correct? A. A single table is best practice for similar data. Using the index and timestamp in the row key groups and indexes data contiguously, supporting efficient queries for recent prices. Why are the others incorrect? B. Relying solely on a reverse timestamp as the row key without the index scatters data, preventing efficient querying for a specific index. C. Creating a separate table for each index is a Bigtable anti-pattern. Similar data should reside in a single table to avoid unnecessary overhead. D. Creating separate tables for each index is an anti-pattern in Bigtable, causing unnecessary management overhead and complexity.
You are building a report-only data warehouse where the data is streamed into BigQuery via the streaming API. Following Google's best practices, you have both a staging and a production table for the data. How should you design your data loading to ensure that there is only one master dataset without affecting performance on either the ingestion or reporting pieces? The options are: Option A, have a staging table that is an append-only model, and then update the production table every 3 hours with the changes written to staging. Option B, have a staging table that is an append-only model, and then update the production table every 90 minutes with the changes written to staging. Option C, have a staging table that moves the staged data over to the production table and deletes the contents of the staging table every 3 hours. Option D, have a staging table that moves the staged data over to the production table and deletes the contents of the staging table every 30 minutes.
To arrive at the correct answer, we focus on the keywords: streamed into BigQuery via the streaming API, staging, and a production table, only one master dataset, without affecting performance.
The correct answer is option C, Have a staging table that moves the staged data over to the production table and deletes the contents of the staging table every 3 hours.
Why is this correct? C. BigQuery's streaming buffer retains data for up to 90 minutes, preventing DML operations like deletes. Moving data to production and deleting from staging every 3 hours safely avoids this limitation and maintains a single master dataset. Why are the others incorrect? A. Maintaining an append-only staging table without deleting processed records creates duplicate data across staging and production, failing the requirement to maintain only one master dataset. B. An append-only model fails to maintain a single master dataset. Additionally, 90 minutes is the exact upper bound of the streaming buffer, making operations risky. D. Data in BigQuery's streaming buffer cannot be deleted for up to 90 minutes. Attempting to delete staging data every 30 minutes will fail due to these streaming buffer restrictions.
You issue a new batch job to Dataflow. The job starts successfully, processes a few elements, and then suddenly fails and shuts down. You navigate to the Dataflow monitoring interface where you find errors related to a particular DoFN in your pipeline. What is the most likely cause of the errors? The options are: Option A, job validation. Option B, exceptions in worker code. Option C, graph or pipeline construction. Option D, insufficient permissions.
To arrive at the correct answer, we focus on the keywords: starts successfully, processes a few elements, fails and shuts down, errors related to a particular DoFN.
The correct answer is option B, exceptions in worker code.
Why is this correct? B. The pipeline started and processed elements, indicating job submission and construction succeeded. Errors pointing to a particular DoFN indicate an exception thrown by the worker code during execution. Why are the others incorrect? A. Job validation issues would prevent the job from starting successfully or processing any elements. C. Graph or pipeline construction errors occur during job submission, preventing the job from starting or processing elements. D. Insufficient permissions typically fail the job at submission or upon initial access to resources, not after successfully processing a few elements.
Your new customer has requested daily reports that show their net consumption of Google Cloud Compute resources and who used the resources. You need to quickly and efficiently generate these daily reports. What should you do? The options are: Option A, do daily exports of cloud logging data to BigQuery. Create views filtering by project, log type, resource, and user. Option B, filter data in cloud logging by project, resource, and user, then export the data in CSV format. Option C, filter data in cloud logging by project, log type, resource, and user, then import the data into BigQuery. Option D, export cloud logging data to cloud storage in CSV format. Cleanse the data using data prep, filtering by project, resource, and user.
To arrive at the correct answer, we focus on the keywords: daily reports, net consumption of Google Cloud Compute resources, who used the resources, quickly and efficiently.
The correct answer is option A, do daily exports of cloud logging data to BigQuery. Create views filtering by project, log type, resource, and user.
Why is this correct? A. Creating a sink to automatically export cloud logging data to BigQuery is the most efficient, native solution for log analysis. BigQuery views then allow you to easily query and generate the required daily reports. Why are the others incorrect? B. Manually filtering and exporting CSVs is not an automated or efficient approach for generating recurring daily reports. C. Data cannot be directly imported into BigQuery from a filtered cloud logging view. An automated export sync must be configured. D. Using cloud storage and data prep adds unnecessary steps, cost, and complexity when BigQuery export syncs can handle this directly and more efficiently.
Refer to the attached Picture 1, reference exhibit. The development and external teams have the project viewer identity and access management (IAM) role in a folder named visualization. You want the development team to be able to read data from both cloud storage and BigQuery, but the external team should only be able to read data from BigQuery. What should you do? The options are: Option A, remove cloud storage IAM permissions to the external team on the Acmera data project. Option B, create virtual private cloud (VPC) firewall rules on the Acmera data project that deny all ingress traffic from the external team's CIDR range. Option C, create a VPC service controls perimeter containing both projects and BigQuery as a restricted API. Add the external team users to the perimeter's access level. Option D, create a VPC service controls perimeter containing both projects and cloud storage as a restricted API. Add the development team users to the perimeter's access level.
To arrive at the correct answer, we focus on the keywords, project viewer, folder named visualization, the development team to be able to read data from both cloud storage and BigQuery, external team should only be able to read data from BigQuery.
The correct answer is option D, create a VPC service controls perimeter containing both projects and cloud storage as a restricted API. Add the development team users to the perimeter's access level.
Why is this correct? D. VPC service controls can restrict access to the cloud storage API. By restricting it and adding only the development team to the access level, they gain access. BigQuery remains unrestricted, allowing both teams to access it via their inherited folder-level IAM viewer roles. Why are the others incorrect? A. IAM permissions are inherited hierarchically from the folder. You cannot remove or explicitly deny IAM roles at a lower, project, level if they are already granted at a higher, folder, level. B. VPC firewall rules manage network traffic for Compute Engine VM instances. They do not control or restrict access to managed Google Cloud APIs like Cloud Storage or BigQuery. Why are the others incorrect? C. Restricting BigQuery and adding the external team to the access level would block the development team from BigQuery. It also leaves cloud storage unrestricted, allowing the external team to read it.
Your startup has a web application that currently serves customers out of a single region in Asia. You are targeting funding that will allow your startup to serve customers globally. Your current goal is to optimize for cost, and your post-funding goal is to optimize for global presence and performance. You must use a native JDBC driver. What should you do? The options are: Option A, use Cloud Spanner to configure a single region instance initially, and then configure multi-region Cloud Spanner instances after securing funding. Option B, use a Cloud SQL for PostgreSQL highly available instance first, and Bigtable with US, Europe, and Asia replication after securing funding. Option C, use a Cloud SQL for PostgreSQL zonal instance first, and Bigtable with US, Europe, and Asia after securing funding. Option D, use a Cloud SQL for PostgreSQL zonal instance first, and Cloud SQL for PostgreSQL with highly available configuration after securing funding.
To arrive at the correct answer, we focus on the keywords, single region in Asia, optimize for cost, optimize for global presence and performance, native JDBC driver.
The correct answer is option A, use Cloud Spanner to configure a single region instance initially, and then configure multi-region Cloud Spanner instances after securing funding.
Why is this correct? A. Cloud Spanner supports single region deployments for lower initial costs, seamlessly scales to multi-region for global performance without schema changes, and supports a native JDBC driver. Why are the others incorrect? B. Bigtable is a NoSQL database that does not support a native JDBC driver, and migrating from PostgreSQL to Bigtable would require significant application rewrites. C. Bigtable lacks native JDBC driver support and is a NoSQL database, making migration from Cloud SQL complex and unsuitable for the requirements. D. Cloud SQL for PostgreSQL is primarily a regional database. Its high availability configuration does not provide the global active-active read/write capabilities needed for global performance.
You need to migrate 1 PB of data from an on-premises data center to Google Cloud. Data transfer time during the migration should take only a few hours. You want to follow Google recommended practices to facilitate the large data transfer over a secure connection. What should you do? The options are: Option A, establish a cloud interconnect connection between the on-premises data center and Google Cloud, and then use the storage transfer service. Option B, use a transfer appliance and have engineers manually encrypt, decrypt, and verify the data. Option C, establish a cloud VPN connection, start cloud compute SCP jobs in parallel, and run checksums to verify the data. Option D, reduce the data into 3 TB batches, transfer the data using SUDL, and run checksums to verify the data.
To arrive at the correct answer, we focus on the keywords: 1 PB of data, from an on-premises data center to Google Cloud, only a few hours, secure connection.
The correct answer is option A, establish a cloud interconnect connection between the on-premises data center and Google Cloud, and then use the storage transfer service.
Why is this correct? A. Cloud Interconnect provides a dedicated, high-bandwidth connection required to transfer 1 PB of data within a few hours. Storage transfer service is the recommended, fully managed service for large-scale data transfers over this connection. Why are the others incorrect? B. Transfer appliance involves physical shipping of the appliance, which typically takes days or weeks, violating the strict requirement to complete the transfer in only a few hours. C. Cloud VPN has a maximum throughput that is insufficient to transfer 1 PB in a few hours. Additionally, Cloud Compute SCP is not the recommended tool for managing petabyte-scale data transfers. D. Transferring 1 PB using SUDL without a dedicated high-bandwidth connection will not meet the time requirement. Furthermore, manually managing 3 TB batches is inefficient and not a Google recommended practice for this scale.
You are loading CSV files from cloud storage to BigQuery. The files have known data quality issues, including mismatched data types, such as strings int64s in the same column, and inconsistent formatting of values such as phone numbers or addresses. You need to create the data pipeline to maintain data quality and perform the required cleansing and transformation. What should you do? The options are: Option A, use Data Fusion to transform the data before loading it into BigQuery. Option B, use Data Fusion to convert the CSV files to a self-describing data format, such as AVRO, before loading the data to BigQuery. Option C, load the CSV files into a staging table with the desired schema, perform the transformations with SQL, and then write the results to the final destination table. Option D, create a table with the desired schema, load the CSV files into the table, and perform the transformations in place using SQL.
To arrive at the correct answer, we focus on the keywords: loading CSV files from cloud storage to BigQuery, data quality issues, mismatched data types, inconsistent formatting, cleansing and transformation.
The correct answer is option A, use Data Fusion to transform the data before loading it into BigQuery.
Why is this correct? A. Cloud Data Fusion, specifically the Wrangler workspace, provides a visual interface for easily building pipelines that perform complex data cleansing, parsing, and transformation before loading into BigQuery. Why are the others incorrect? B. Converting CSV to AVRO does not perform the required data cleansing or resolve the underlying formatting and type mismatch issues present in the source files. C. Loading mismatched data types, like strings and int64s in the same column, directly into a BigQuery staging table will fail because BigQuery enforces strict schema typing during the load job. D. Loading messy data directly into a BigQuery table with a desired schema will fail due to schema validation errors when BigQuery encounters mismatched types.
You are developing a new deep learning model that predicts a customer's likelihood to buy on your e-commerce site. After running an evaluation of the model against both the original training data and new test data, you find that your model is overfitting the data. You want to improve the accuracy of the model when predicting new data. What should you do? The options are: Option A, increase the size of the training dataset and increase the number of input features. Option B, increase the size of the training dataset and decrease the number of input features. Option C, reduce the size of the training dataset and increase the number of input features. Option D, reduce the size of the training dataset and decrease the number of input features.
To arrive at the correct answer, we focus on the keywords: overfitting the data, improve the accuracy of the model when predicting new data.
The correct answer is option B, increase the size of the training dataset and decrease the number of input features.
Why is this correct? B. Increasing the training dataset size provides more examples for the model to learn generalized patterns. Decreasing the number of input features reduces model complexity, preventing it from memorizing noise in the training data. Why are the others incorrect? A. While increasing the training dataset size helps, increasing the number of input features adds to model complexity, which can exacerbate overfitting. C. Reducing the size of the training dataset provides fewer examples to learn from, and increasing input features adds complexity, both of which worsen overfitting. D. Although decreasing the number of input features helps reduce complexity, reducing the training dataset size gives the model fewer examples, which can negatively impact its ability to generalize.
You are implementing a chatbot to help an online retailer streamline their customer service. The chatbot must be able to respond to both text and voice inquiries. You are looking for a low-code or no-code option, and you want to be able to easily train the chatbot to provide answers to keywords. What should you do? The options are: Option A, use the Cloud Speech-to-Text API to build a Python application in App Engine. Option B, use the Cloud Speech-to-Text API to build a Python application in a Compute Engine instance. Option C, use Dialogflow for simple queries and the Cloud Speech-to-Text API for complex queries. Option D, use Dialogflow to implement the chatbot, defining the intents based on the most common queries collected.
To arrive at the correct answer, we focus on the keywords: chatbot, respond to both text and voice inquiries, low-code or no-code option, easily train the chatbot to provide answers to keywords.
The correct answer is option D, use Dialogflow to implement the chatbot, defining the intents based on the most common queries collected.
Why is this correct? D. Dialogflow is a managed, low-code/no-code platform specifically designed for building conversational interfaces, chatbots. It natively supports both text and voice interactions and uses intents to easily map user keywords to responses. Why are the others incorrect? A. Building a custom Python application involves significant coding, which violates the requirement for a low-code or no-code option. Additionally, the speech-to-text API only transcribes audio and does not manage chatbot logic. B. Developing a custom application on Compute Engine requires substantial coding and infrastructure management, contradicting the low-code requirement. It also lacks built-in conversational logic. C. Dialogflow already natively incorporates speech recognition capabilities and can handle complex queries. Unnecessarily splitting the architecture adds complexity without providing any benefits over using Dialogflow alone.